Okay, let's unpack this. Imagine a piece of hardware that isn't fixed, isn't permanent, but can literally change its mind. It becomes whatever you need it to be after it's been manufactured. Sounds a bit like magic, right? Like it's some kind of shape-shifting circuit.
Yeah, it does sound like magic, but what's fascinating here is that it's not. It's really just incredible engineering. Today, we're taking a deep dive into field programmable gate arrays, or FPGAs.
FPGAs.
We'll
Yeah.
peel back the layers, explore what they are, how they're built inside, and crucially, why they've become so powerful in modern electronics. We'll cover the fundamentals right through to how you actually, configure them to do these amazing things.
Okay. So our mission for you today is really to cut through the jargon. We want to give you those aha moments about FPGAs. So you'll walk away, hopefully, well-informed and maybe a little inspired by just how versatile these things are. We want you to get not just what they are, but why they matter so much. You see them everywhere now, from data centers to, well, aerospace. So let's start with the absolute basics then. What exactly is an FPGA, and why is this idea of being programmable after manufacturing such a big deal?
Okay, so at its core, an FPGA is a programmable logic device. The key phrase, like you said, is programmable. Unlike a lot of chips that come from the factory doing one specific thing, an FPGA is designed so that you, the user, can program it, or even reprogram it after it's been made.
After it's made, wow.
Think of it like a huge interconnected grid. It's got generic logic blocks and pathways all over it, and you can customize these to perform pretty much any digital operation you can think of.
Yeah.
That gives you incredible adaptability.
Okay, that idea, defining its function after it's built, that sounds unbelievably flexible. So how does that stack up against something like an ASIC, an application-specific integrated circuit? Many people have probably heard of those. Where do FPGAs fit in?
Right, that's a really crucial distinction. It gets right to the heart of why FPGAs even exist. FPGAs offer, well, unparalleled flexibility
Right.
and reprogrammability. You buy the chip, a sort of generic chip, then you define its function using software tools.
Okay.
It's a complete contrast to ASICs. An ASIC is custom designed, custom fabricated for one single specific job. Once that ASIC is manufactured, its design is fixed. It's literally etched into the silicon permanently. It's built to do one thing extremely well, very fast, very efficiently, but just that one thing.
Huh. So if an ASIC is like getting a custom suit tailored perfect for one event, but, expensive and totally unchangeable, then an FPGA is more like a high-tech modular wardrobe,
Yeah.
something you can reconfigure every day.
That's a great analogy, exactly. And that versatility is why FPGAs are becoming so critical in, well, all sorts of cutting-edge fields. Take rapid prototyping, for instance. You can test and iterate on a hardware design super quickly. You don't have the huge cost and the massive time delay of fabricating a new custom chip every single time you want to tweak something.
Right, that makes sense for development.
Yeah, and they're essential in things like software-defined radio, too, where communication standards are always evolving. Or even in mission-critical systems, think satellite communications, where you might actually need to reconfigure hardware mid-flight.
Wow.
And we're seeing them more and more in AI, artificial intelligence, and machine learning accelerators. Algorithms there change so fast, the hardware needs to keep up. This blank canvas ability means they can adapt to new challenges, new standards almost instantly.
Okay, so it really is like that blank canvas chip. You can paint your circuit onto it, wipe it clean, paint another one. Unlike a pre-printed ASIC, that flexibility is clearly a massive advantage. Rapid prototyping, updates, adaptation in the field. But, okay, to make this painting happen, you need a way to tell the FPGA what circuit you want. How do designers actually program these things?
Good question. The most common way is by using hardware description languages, HDLs. The big ones you hear about are VHDL and Verilog.
VHDL and Verilog. Okay. Are they like normal programming languages like Python or C++?
Not exactly. They're different because they're designed to describe hardware. Instead of sequential instructions, you're describing the behavior and the structure of digital circuits. You're essentially defining logic gates, registers, how things are connected, but at a reasonably high level.
So you're describing the circuit, not just writing code.
Precisely. And then specialized software tools take that description
Right.
and translate it into the actual physical configuration for the FPGA's internal resources.
Yeah.
It's a really powerful way to define complex hardware without having to manually draw, every single wire and gate.
That blank canvas idea really sticks. So if we're painting this circuit, What are the actual, like, brushes and colors inside the chip? What allows for this incredible reconfigurability? How are these amazing devices actually built on the inside? Let's get into that.
Okay, yeah, this is where the internal architecture gets really clever. The main FPGA architecture is basically a huge grid. It's made up of what are called configurable logic blocks, or CLBs.
CLBs, right.
Think of CLBs as the main building blocks. They're scattered all across the chip, and each one can perform a small piece of logic. Alongside these CLBs, you've got I/O pads around the edges. That's for talking to the outside world. And critically, there's this network of routing channels connecting everything together.
Okay, so CLBs do the thinking, I/O talks outside, and routing connects it all up.
Pretty much. And each CLB can be tailored, programmed to execute a really wide variety of specific logic functions. It's a very modular way to build up complex digital systems.
And inside these CLBs, I think you mentioned something called a lookup table, a LUT. That sounds pretty fundamental. What are the key bits inside a CLB, and how does this LUT thing actually work? It sounds like it's right at the heart of the reconfigurability.
It really is. Yeah, the LUT is absolutely crucial within a CLB. So typically, each CLB will contain several key elements. You'll usually find a four-input lookup table, or LUT, often a full adder, for doing math,
Mm-hmm.
and a knee-type flip-flop for memory for storing state.
Okay, a LUT, an adder, and a flip-flop. What's special about the LUT?
Well, the fascinating thing about the LUT is it's not really a calculator in the way you might think. It's literally a small piece of memory. Imagine it like a tiny, super fast cheat sheet, or maybe a truth table stored in memory.
A cheat sheet.
Yeah, you give it a set of inputs, say 4 binary inputs for a 4-input LUT, and it instantly just looks up the correct output based on whatever pattern is programmed into its memory table.
Ah, okay, so it's pre-programmed with the answers for every possible input combination.
Exactly. And the real genius is that this cheat sheet, this memory table, can be completely rewritten when you configure the FPGA. So one moment, you can program it to behave like a simple A and D gate. The next moment, you reconfigure it, and now it acts like an OR gate, or maybe even part of a more complex arithmetic function. This dynamic programmability, being able to change the function of these tiny blocks, that's what gives FPGAs their incredible internal flexibility.
Wow, so it's like a tiny programmable logic puzzle piece. You can just reconfigure it on the fly to do different calculations or logic. That internal flexibility is really quite remarkable. You can build exactly the digital circuit you need right down at a very low level.
Okay, so you've got these incredibly versatile logic blocks, the CLBs with their LUTs, but how do they all talk to each other? How does a signal get from, say, one CLB over here to another one way over on the other side of the chip?
Right. That's where the programmable interconnects come in. And honestly, they're just as critical as the CLBs themselves. FPGAs have this vast reconfigurable grid of these interconnect wires and switches. This grid lets designers establish connections between basically any of the CLBs on the chip.
So it's like a customizable wiring system.
Exactly. This grid is what lets you create complex data paths, control structures, all across the chip. It makes all those individual blocks behave like one single cohesive circuit. A really key part of this interconnect system is something called the switch matrix or switch box.
Switch matrix. Yeah. Think of it like a programmable railway junction, or maybe a telephone switchboard. It sits at the intersections of the routing channels and allows signals to be directed precisely where they need to go. It connects signals between all those CLBs, letting you build really complex logic circuits by hooking up these blocks in almost any pattern you can imagine.
Okay, so that's the internal communication network, like a customizable highway system for data inside the chip. But what about getting information out of the FPGA or into it? How does it actually connect to other devices? Maybe a sensor, another chip, a screen?
Good point. For that, you rely on the I/O blocks, input-output blocks. These are the crucial interface. They link the internal FPGA logic to the external world, the environment outside the chip.
And where are they located?
They're usually arranged around the perimeter, the edges of the FPGA chip. And importantly, they are highly configurable themselves, too. They contain different kinds of buffers. Input buffers for signals coming in, output buffers for signals going out, and also bidirectional buffers for signals that need to travel both ways.
Okay, so they handle the translation to the outside world.
Exactly. These I/O blocks are designed to handle communication with all sorts of external devices. They make sure the signals are compatible, handling different voltage levels, different communication standards. So yeah, you've got the internal logic in the CLBs, the interconnect pathways between them, and then these I/O blocks as the gateways to the outside. A complete customizable system.
It's really clear how this whole architecture allows for just incredible flexibility in what an FPGA can do. But we've talked about the components, how they're connected. We understand the theory, I think. So let's get practical. How do we, as designers, actually tell this highly flexible chip what we want it to do? What's the real world process? How do you bring a design to life?
Right. So to define what the FPGA does, a designer usually starts by writing their design in a hardware description language. An
Mm.
HDL, we mentioned them before, VHDL, Verilog, or maybe System Verilog.
Okay, so you start with code,
Yeah.
essentially.
Yeah, pretty much. While you can use schematic design, drawing the circuit visually, for simpler stuff, HDL is really the industry standard for anything large or complex. It lets you specify the high-level functional behavior. You don't have to manually draw every single component, which would be impossible for modern designs. Think of the HDL code as the blueprint for your digital circuit.
Okay, so you've written your HDL blueprint. What's the journey from that abstract idea, that code, to a working, configured FPGA chip? It sounds like there must be quite a few steps involved.
There are, yeah. And it's a fascinating process, usually managed by some pretty powerful software tools. First, you'll use what's called an electronic design automation tool, an EDA tool.
EDA tool, but yeah.
This tool takes your HDL code and performs a step called synthesis, or sometimes technology mapping. Synthesis basically translates your high-level design description into something called a netlist.
A netlist.
Yeah, a netlist is essentially a lower-level description of your design. It brings it down into the specific logic elements that are actually available on the FPGA you're targeting. Things like those CLBs and LUTs we were talking about earlier. It maps your abstract design onto the real hardware building blocks.
Right, so the EDA tool translates the blueprint into a list of actual parts needed from the FPGA.
Exactly. Then comes a really crucial step called place and route. This is typically done by proprietary software provided by the FPGA company itself, the vendor.
Place and route sounds descriptive.
It is. During placement, the software decides exactly where on the physical silicon chip each logic element from your netlist is going to sit. Then, during routing, it figures out precisely how all these placed elements will be connected using that programmable interconnect grid we discussed.
Ah, so it's like arranging the furniture and then wiring everything up.
That's a decent analogy.
Yeah.
And it's a highly complex optimization puzzle. The software tries to place and route things for the best performance, like the highest clock speed, and to use the chip's resources efficiently.
Okay, so after place and route, is it done?
Not quite. Before you commit, the designer has to validate the results. This is absolutely critical. It involves doing thorough timing analysis. Does the circuit run fast enough? Will it meet the required clock speed? You also run various simulations to check the functionality. Does it actually do what it's supposed to do? And there are other verification and validation techniques too. You need to be really sure everything works as intended before you actually program the chip. This validation loop can take a fair bit of time and effort on a real project.
Makes sense. You don't want to program faulty hardware.
Definitely not. So after this rigorous design and validation process is complete, then a special binary file is generated. This file is often called a bitstream. It's the final, precise blueprint that tells every configurable element inside the FPGA exactly how it should be set up.
The bitstream. That's the magic file.
That's the one. This bitstream is then transferred to the FPGA device. Usually this happens via a standard serial interface, most commonly JTAG, that stands for Joint Test Action Group. Or sometimes the bitstream is loaded onto an external memory chip like an EEPROM, which sits next to the FPGA. Then when the system powers up, the FPGA automatically reads the bitstream from that memory and configures itself. It's this bitstream that actually transforms the blank, generic FPGA into your custom hardware circuit.
That's incredible how a text description, your HDL code, or maybe a drawing transforms through all these steps into an actual physical circuit configuration on the chip. It really is a true bridge between the software world of design and the hardware world of silicon, turning logic into tangible electronic paths.
Okay, given this whole complex design flow, synthesis, place and route, validation, bitstream, what are some of the actual software tools engineers use day to day to make all this happen? Yeah, there are several major, pretty powerful software suites that engineers rely on for this whole process. Designing, synthesizing, implementing, configuring. Some big examples include Vivado, that's from Xilinx, which is now part of AMD. Then there's Quartus Prime, that's from Intel's FPGA division, which used to be Altera.
Vivado and Quartus. Okay.
Those are the big two from the main vendors for the whole flow. Then for simulation, which is critical for verification, you often see tools like ModelSim. ModelSim is from Mentor Graphics, which is now Siemens EDA.
Mhm.
And another widely used simulator is VCS from Synopsys. These sophisticated tools are really the workhorses that make designing complex FPGAs possible. Honestly, without them, it would be practically impossible today.
Right, you need that automation. And who are the big companies actually making these versatile chips? Which names should our listeners be aware of if they're looking into FPGAs or maybe just seeing them mentioned in tech news?
Well, there are several major companies that specialize in designing and manufacturing FPGAs. Each one has its own unique families of chips, its own development tools like Vivado or Quartus, and its own support ecosystem. The two biggest players, the ones you'll hear about most often, especially for high-performance stuff, are definitely Xilinx, now part of AMD, as I mentioned,
Right. AMD.
and Intel Corporation with their FPGA group that came from acquiring Altera.
Intel. Okay, so AMD and Intel are the giants here too.
They are the two dominant ones, yeah.
Hmm.
But beyond them, there are other really significant vendors contributing a lot of innovation. You've got Lattice Semiconductor. They often focus on low-power FPGAs, mid-range devices. There's Microchip Technology. They acquired a company called Microsemi, and they offer a range of FPGAs, sometimes for more specific niche or maybe high-security applications.
Okay.
Then there's Acronex Semiconductor. They're known for very high-performance FPGAs, often targeting data centers and AI acceleration. QuickLogic Corporation specializes in ultra-low-power FPGAs, often for mobile or battery-powered devices. And you also have companies like Aldec Inc. They provide a variety of EDA tools, including simulators, specifically for FPGA design. So it's quite a competitive field, constantly evolving.
So definitely a vibrant field then. Lots of specialized companies pushing this incredible technology forward. Wow. Okay, we've covered a lot of ground. We've gone from the core concept, what is a field programmable gate array? We've unpacked its internal architecture, those clever CLBs and LUTs. We understand how signals flow through the routing interconnects, how it talks to the outside world using the I/O blocks, and we've walked through the entire design and configuration process, from HDL code to Bitstream, right down to the specific software tools and the major companies making these chips.
Yeah, we really have. And if we try to connect this all back to the bigger picture, this ability to reprogram hardware basically on the fly, it just opens up possibilities far beyond what traditional fixed function chips can ever do. Think about how quickly software evolves, right? Now imagine hardware that can actually evolve along with it, even after it's been shipped and deployed out in the field.
That's powerful.
It really is. And it raises an interesting question, maybe something for you listening to think about. What stands out most to you about how adaptable these FPGA devices are? And thinking ahead, what kind of new applications might this incredible flexibility enable in the future, especially as technology just keeps accelerating?
That's a great thought to end on. Thanks so much for walking us through all of that. And thanks to all of you for joining us on this deep dive into the fascinating world of FPGAs. Until next time, keep exploring.